Recall earlier lessons where we learned about the different sizes of atoms. In any row, greater charge in the nucleus pulls electrons closer to the nucleus. We've learned about atomic excitation and how atoms emit photons when their electrons jump from one energy level to another. Here we depict three of many energy levels in an atom. An electron jumping from the third level to the second level emits a red photon. An electron jumping from the second level to the ground state emits a green photon. And an electron jumping from the third level to the ground state emits an ultraviolet photon, shown here as blue. The energy of this jump equals the sum of the energies of the red and green photons. And it follows that the sum of the frequencies for the red and green photons equals the frequency of the ultraviolet photon. Quite yum! The idea that electrons may occupy only certain levels was first suggested by Niels Bohr in 1913. Yet it was very perplexing to him and other early investigators. It was perplexing because the electron at the time was thought to be a particle whirling around the nucleus like a planet whirls around the sun. Just as any kind of satellite can orbit at any distance from the sun, it would seem that an electron should be able to orbit at any radial distance around the nucleus, depending, of course, like the satellite, on its speed. If electrons moved randomly among all orbits, they'd emit all frequencies of light. But this doesn't happen. If it did, an electron accelerating in a circular path would continually radiate energy. And this loss of energy would cause it to spiral into the nucleus. Again, this doesn't happen. Why the electron occupies only specific levels is understood by considering the electron to be not a particle, but a wave. Recall in our previous lesson how Louis de Broglie introduced the concept of matter waves. He hypothesized that a wave is associated with every particle, and that the wavelength of a matter wave is inversely proportional to a particle's momentum. These matter waves behave just like other waves. They can be reflected, refracted, diffracted, and caused to interfere. Using the idea of interference, de Broglie showed that the discrete values of radii of Bohr's orbits, that is, separate and distinct orbits, are a natural consequence of standing electron waves. As seen in A, an orbiting electron forms a standing wave only when the circumference of its orbit is equal to a whole number multiple of the wavelength. When the wave does not close in on itself in phase, shown in B, it undergoes destructive interference. So in this view, orbits exist only where the waves close in on themselves in phase. Hence, we visualize the electron orbits in an atom having specific radii because the circumferences of the orbits are whole number multiples of the electron wavelength. This results in a specific energy state for each orbit. The art here is greatly oversimplified because in reality the standing waves make up spherical and ellipsoidal shells rather than flat circular ones. The electron wave becomes a standing wave, like a wave on a musical string. We view the electron not as a particle located at some point in the atom, but as if its mass and charge was spread out into a standing wave surrounding the atomic nucleus, with an integral number of wavelengths fitting evenly into the circumferences of the orbits. The circumference of the innermost orbit, according to this picture, is equal to 1 wavelength. The second orbit has a circumference of 2 electron wavelengths, the third 3, and so forth. For each orbit, the electron has a unique speed which determines its wavelength. Since the circumference of electron orbits are separate and distinct from one another, which is to say discrete, it follows that the radii of these orbits, and hence the energy levels, are also discrete. As long as an electron carries the momentum necessary for wave behavior, atoms don't shrink in on themselves. Yum quantum physics. In the still more modern wave model of the atom, electrons move not only around the nucleus, but also in and out, toward and away from the nucleus. The electron wave is spread out in 3 dimensions, leading to the picture of an electron cloud. This is a cloud of probability, not a cloud made up of a pulverized electron scattered over space. The electron, when detected, remains a point particle. An Austrian physicist, Erwin Schrödinger, formulated an equation that describes how matter waves change under the influence of external forces. Schrödinger's equation plays the same role in quantum mechanics that Newton's equation, acceleration equals force per mass, plays in classical physics. We show the equation here. Textbook author and colleague Art Hobson displays the Schrödinger equation in his classroom. Later study, not now, will lead to an understanding of this important quantum equation if you decide to enter deeper into the quantum world. Don't expect the same degree of understanding with quantum mechanics that you may enjoy with classical mechanics. I remember struggling with quantum mechanics in graduate school, thinking I was defective because it didn't gel like classical mechanics did. At that time, I wasn't aware of the quote by Richard Feynman. I think it is safe to say that nobody understands quantum mechanics. And Feynman won a Physics Nobel Prize for his work on the quantum. In any event, most physicists view quantum mechanics as a fundamental theory of nature. But not all physicists. Interestingly enough, Albert Einstein, one of the founders of quantum physics, never accepted it as fundamental. He considered the probabilistic nature of quantum phenomena as the outcome of a deeper, yet undiscovered physics. This is what he had to say. Although Einstein practiced no religion, he often invoked God as the old one in his statements about the mysteries of nature. For Einstein, God was spelled N-A-T-U-R-E, nature. Our screencasts on quantum physics have only scratched the surface, but they're a beginning for those of you who wish to go further into the world of the quantum. I want to leave you with a question. Consider an electron ejected from a metal surface by a photon. Then consider an electron occupying an energy state in an atom. In which case does it behave more as a particle, and in which more as a wave? Until next time, good energy.